And I don't check for the undergraduate courses. They're pretty much all the same. Quizzes once a week, one midterm, one final. In this case, you get project. You may get some extra credit stuff. I really just encourage people to please do the homework in a timely fashion before the next meeting period. Because getting behind, especially 2 lectures behind in the summer, you can be so, you wouldn't believe how far behind you can get. It's worse than random. Now, you're in random. But in my opinion, random's the one that'll really kill you if you get behind. How many have had random in here? Okay. Did you have it this spring semester?
I had it 2 semesters ago.
All right, it can be a rough course.
Yeah, it was nothing.
I tell people this straight up, that in my opinion, the most conceptually abstract and difficult course for undergrad, if it's taught right, is random signals and systems. Probably the one that should be the most obvious to everybody who's an electrical engineer, circuits. If you don't get circuits, leave. Talk to Dave Irwin about that. He doesn't use those terms as well. Get out.
He was pretty straightforward. He was like,
He's pretty funny. He's the best circuits teacher I've ever seen.
Yeah.
I've seen a lot. All right. So this is the text. Now, let me try this one. How many have this text? Raise your hands. Does anybody not have this text? I take it, do you have the text or not? Do you have this text? You do? Do you have this? Okay. Anybody not have it?
I have a PDF of it, but same thing.
Yeah, we have yes.
All right. It is closed book, closed notes. I try to tell people, get the book so you can write it. This one's a disaster, but I mean, my texts that I went through the undergraduate are just written up like you wouldn't believe it, because sometimes I have to think, I don't know how to do that, but I remember I did it one time. It's in Radestein or Resnick or something like this. And especially in the graduate course, graduate text, you're going to see you ink them up like you wouldn't believe it. So if you've had EMAG 1, and EMAG 2 is time-varying electromagnetics. It starts in chapter 5. So what I'm planning on doing is first I'm going to put down Maxwell's equations, mention a few things about the coupling equation. These are things you have to know well and understand. Then we're going to develop what's called the wave equation. Now, in physics, they don't deal with a lot of this stuff at the level we're going to. This is an applications course, and we're going to talk about everything that's involved, but typically at constant frequencies. There are time-varying phenomena that aren't at a given frequency, but not a whole lot. So here's what we're going to start with, Maxwell's equations. And for Maxwell, this is James Clerk Maxwell. He's probably, as far as his contributions to basic understanding of electromagnetics, he's the greatest. He actually, if you look through his treatise on electromagnetics, he actually figured out the speed of light before the measurements and stuff, but it was based on some assumptions. So with Maxwell's equations, there are really 2 of them, and it's curl of H, and H is a magnetic field, is equal to J plus the partial of B with respect to T. That's the first. Does anybody remember the name of this equation? It's named for, all these are named for people.
that's
Amperes.
Who is it? What, Michael Faraday's law of induction? That's
Ampere's law.
Ampere's law, right? Ampere's law. All right. Now that's one of them. The second one is Michael Faraday's law of induction. Its curl of E is equal to minus dB dt. Those are the actual time domain forms that are valid in general. They're valid in all dimensions, even at the quantum levels. You can find that these things work. Now, we get down to it. There's coupling equations that relate these variables. The first is J. J is actually a current density, so it's amps per meter squared, and it's really equal to sigma times the E field. E would be volts per meter. I'll get all this out there. Y'all remember that class? Now after that, there's also D. It's equal to epsilon E. And here it relates the D field and coulombs per meter squared to the E field, which is in volts per meter. Do y'all remember some of this stuff, right? And epsilon, sigma is called the conductivity. Epsilon is the permittivity. Permittivity. And finally, you get V is equal to mu H. Now, mu is actually the permeability. And I better say something else. There are a couple of constants you'll see appearing all the time. Epsilon, well, first is epsilon naught, which is about 8.854 times 10 to the minus 12 farads per meter. Then there's mu zero, which is 4 pi times 10 to the minus 7th, and that's henries per meter. Sigma can have all sorts of values from 0 up to, I don't know, 5 times 10 to the 8th, 5 times 10 to the 7th, and that would be in 1/ohm meters. But usually the thing you have to remember is mu, the permeability, is equal to a relative permeability times mu naught, and epsilon is equal to some epsilon relative times epsilon naught. I'm putting these down here so everybody just has it. Try to jog your memory if you haven't had it for a while. Both mu naught and mu relative and epsilon relative or something, it gives you an idea of how much more energy, electrostatic or magnetostatic energy, a region can hold compared to a vacuum for a given value of either H or E. Now, do you all remember this kind of, right? Yeah. So these are just general things that you have to know. This is the time domain form of Maxwell's equations. Most engineers prefer this. When you did circuit analysis, your primary tool to do circuit analysis was the phasor domain. You did not write differential equations to get the general solution unless it was for the transient stuff. Almost everything that we do has a direct application for a constant frequency. So what we do is go to the phasor domain. And I think you know what I'm talking about here, but the relationship between time and phasor, I like to do this one time just to make sure everybody has an appreciation. Back in the day when you had circuits, and you had some V of t, I'll make it simple, say it's some V naught cosine of omega naught t. I somehow pushed myself into a corner. And let me actually do this a little better. It's going to be the same thing, but if we have V of t is equal to some V naught cosine of omega naught t, right here. And this is the voltage, and then we have a circuit, we have some resistor, and we have an inductor, and say a capacitor. L would be the value of the inductance, and C would be the value of the capacitor. And this is the kind of thing I tell people, you might get somebody ask you this question if they think you're weak in an area. For instance, say circuit analysis. And they're going to ask you for what is I of t for this. And this, if you interview companies, at least, I can't say what they're going to ask. Companies try to probe you to see what your level of understanding is, because some people really have almost no understanding, and they go to submit a resume, and they're like, why are you here? You can't solve any, did you really graduate? And so I'm trying to tell you what can happen. And this is just as simple as it gets, right? So how do you solve it in the time domain for t? Now, not phasor. You're electrical engineers, not physicists, or mathematicians would write differential equations, right? They're going to say the voltage here is just I times R. The voltage here is L di dt, right? And the voltage here would be what? 1 over C, the integral of I of t, right? Do you all remember that? dt? And then you would write an integral differential equation, set it equal to the voltage source, and solve it for the specific, and for the actual general form and then the specific form. But how do we do it as engineers? That's a very important thing. What is the key? See that? That's constant frequency, right? If it's a constant frequency, we don't do it with a cosine of omega t forcing function. We say that voltage is what? It's a phasor and has a magnitude V naught and an angle 0, right? Can everybody follow me on this one? I'm trying to be as clear as I can. This is how you would do it, because you're not going to waste time writing a whole bunch of differential equations when the solution is trivial if you do it this way. Next, now I'm not worried about the transient solution. If there was a switch there, we'd have to be a little more careful, right? Ain't no switch, it's been on forever. What do you do next? You talk about impedance, right? What's the impedance of an inductor, class?
J omega L.
That's right, J omega L. And what's the impedance of the capacitor?
Negative 1 over 2.
You can just say, yeah, you could say minus J over omega C, right? Not L, but C, correct? All right, now that you have that, if you want the current, it would be in a phasor domain. And to get that current, what would it be? That I, not I of t, but I phasor. You'll see why I'm doing this in a second. I phasor would be what? Well, it would be the voltage V naught, right? At an angle of 0 degrees divided by R plus J omega L, right? And then it would be minus J over omega C. Do you all agree with that? If omega is known, that's what it would be. Correct, class? You'd be able to get a magnitude at an angle. You agree? So at the end of the day, you could say, well, I here, I phasor, has some magnitude, and I'll just call it I naught. And it's at an angle, e to the j angle of I. Can y'all follow me? Got a magnitude and an angle. How many remember how to bring it back to the time domain? That's what the guy will ask you. Do you remember, Kim?
Just insert a e to the j omega t and
Almost, well, you
then take the real part.
Yes, you got it exactly. So what he said is right. To get in the time domain, V of t, you're going to take the real part, some people don't remember this, of the phasor domain, or I should say I of t. I of t, the real part of the phasor domain form, I, and this is going to be I naught, e to the j angle of theta, I, and then you multiply this by e to the j omega t, or j omega naught t, and you take the real part of that. Now, I'm doing it for a reason this way, because a lot of people miss this. You won't believe how many times in class, when I've been dealing with things, radar, things like this, sometimes graduate level courses or doctoral level, and I'm asking for the phasor, take me to the time domain, this is the part that you. So when I do that, I want the real part of this, that means I'm going to start chucking these markers in a second. All right, if I look at this, that means I of t here is equal to the real part of, now I naught is just a scalar value, that comes out front, but then I have e to the j, and here it's going to be omega t plus the phase angle associated with the current. Maybe I'll just put angle associated. So, y'all with me, class? It's supposed to be angle associated with the current. Now, at that point, you use something called Euler's identity. I'll erase it over here, because I'm going to get back to this stuff in a second. Oh, this erase is much better. So, then, I'm going to say this, that anytime you have e to the j, any angle, and you'll need to know this, it can be broken up as cosine of that angle plus j times the sine of that angle. That's called, what's the name for this? Sounds like a well.
Euler's?
Euler. Well, yeah, Euler's. It's spelled E-U, not O-I. All right, that's Euler's thing. So if you look at this, real is cosine. The j means it's imaginary. So when you expand that and take the real part, you get what? I of t becomes simply magnitude of I naught And then it's going to be times cosine of omega t plus the phase angle associated with the current. Now it would be how you get the current there. What I'm just showing you is how to use phasor representation to solve a problem at steady state frequency and then get the actual time domain solution. Can you all follow me in this class? You with me, everybody? So what I'm going to do is use Maxwell's equations. I've got one of them left. And I'm going to get a single equation with a single unknown and solve it. So, but I'm going to do it all in the time domain. And I'm going to use those coupling equations. Take a moment, look at your notes. You see I have D and E related. I have B and H related, and I have J and E related. You all see that? Just take a moment. We're going to go to the time domain, or to the phase domain, sorry. So I'm going to start that over here. I'm going to take curl of H is equal to J. I'll put it back down here, plus the partial of B with respect to T. My first step is to take everything to the phasor domain. Now, just listen to me. How do I take this equation to the phasor domain? The assumption is what? Everything varies as e to the j omega t, correct, class? And that means when I take time derivatives in the time domain become just j omegas in the phasor domain. You all follow me? Everybody? Without going through a formal proof on this, now I get curl of H equals J plus J omega times D. There's nothing magic here. It's just replacing the time derivative with the J omega. Now I use the relationships between J and E and between D and E to get one equation. Really, one equation has two unknowns. I get curl of H here, and it's equal to sigma E plus, and this becomes J omega epsilon E. I hope everybody sees this. It's not tricky. With me? A lot of you have probably seen this, something like this in physics or earlier, and you may want to remember if you guys saw it or not. All right, now what I'm going to do is actually just leave that one alone. And I'm going to go to Michael Faraday's law of induction, and that's curl of E is equal to minus the partial of B with respect to T. Again, nothing new under the sun here, right? What's my next step? Think about what did I do up here next? From here to here, replace the
DDT.
time domain derivative with J omega, correct, class? See it? From here to here. So this becomes simply minus J omega, all right, times B, and then what do I do with B? Did I put it up there? B is
Mu H.
H, right? So finally I get curl of E, and that's equal to minus J omega mu times H. And now, believe it or not, I have two equations with exactly two unknowns, those two. I got Ampere's law, and I got Michael Faraday's law of induction. Now I can go and get one equation with one unknown. We're talking about propagation. This is an important step too. Erase this. We got 2, 4, 6, 8, 10, 11. We're missing a bunch of people, but I guess the rain kept them away. Now, one other thing. I put all the lectures, try to, on, I put them on, make them currently available, but they are on YouTube. Kanan is, he's going to be recording these lectures and putting them on. Are you going to use GroupMe for this?
Yeah.
All right, so you get a GroupMe message from me or him. Did you get all the emails when I sent out the OneNote thing? Just forward it to everybody. And I would encourage you to join. And the thing is this, you can have discussions about anything. Quizzes, tests, you got questions, put them up. I don't frequent those sites. I let you guys alone. But I encourage you to do that because it'll help. if you miss a lecture, possibly you're not sure about something, go, review it. And you guys can correspond with each other because it's helpful at times. Do you guys in the summer have study groups and do you all just work yourself? I don't know what goes on. No? Or that?
It depends.
Well,
Tests, and
I mean, what you can do though, I mean, if you're networking with people, especially you get a whole bunch of people on at the same time studying for a Friday quiz or something, you can ask each other questions, look at old tests, whatever it takes. But it's helpful to interact. I'm going to say that. And it's helpful to also have this recording. Thank you for doing it. All right, back to this thing. So I need one equation with one unknown. That's my starting point. Here's the first equation. Here's the second. I'm going to ask this. Some of you know this answer. I know you. Any ideas? We want one equation with one unknown. When in doubt, take another curl. Take another derivative. Take another, basically try to make one equation look like the other. Just check this out. You see this equation right here. If you look at this for a second, this curl of H is what? That really curl of H there. That's equal to sigma plus j omega epsilon times E. You agree with that? All right, now take a look at this. I got a curl E here. With me? What if I take curl of E? So if I have curl of E, that would be equal to minus j omega mu times curl of H. Hope you all follow me on that. Agree? I must have done this a million times. I've been doing this since I was in undergrad. We used to have to derive everything all the time. And in graduate level courses, this is sort of a staple. Now, at this point, what do you see here? I have something I see here. Right here. Y'all follow me? If I take that curl of H and put it where that curl of H is, now I have an equation with just E. Y'all see this, class? That's the reason to do it. So now I have curl of E is equal to minus j omega mu times curl of H. Well, there's curl of H. Sigma plus j omega epsilon times E. Lo and behold, that's what we wanted. One equation with one unknown. Some of you don't see why. I mean, what's a curl of E? It's not something that you just understand without messing with it. What we have to do is do a vector identity here. How many have had vector calculus here? Did you have Stokes theorem and stuff like that? Okay. Well, this is a standard identity. The curl of E is the gradient of the divergence of E, and it's minus del squared of E. This is just a vector identity. This is still exact. There's no assumptions yet. And that's equal to something, and here we introduce a concept, and this is just generally true in engineering. Anytime you can create one constant that is used over and over again that replaces 10 others or 3 others or 5 others, do it. So if you look here, I have all this stuff that I'm going to be bringing down. So I create a constant that's called gamma. And gamma will have a real part known as alpha and an imaginary part known as beta. And gamma is equal to the square root of j omega mu times sigma plus j omega epsilon. I just want you to know we're still at a constant frequency, but gamma is called a propagation constant. Alpha is an attenuation constant. It's something to give you an idea how fast something decays down. It would be an e to the minus alpha z in our case in a second. Beta is a wave number. It's how many radians per meter of change occurs. All right? Now, I can replace this thing as simply minus gamma squared times e. Take a moment and just convince yourself that what I've done is legit. You agree? I know a lot of this. When you start dealing with curl, and all this mathematics, until you see how the thing actually unfolds and the usefulness of it, it's hard to appreciate. It just is. Circuits are a lot easier to understand when you do a phasor analysis and the actual interpretation, meaning what's measurable. This isn't. Y'all with me, class? Now, here's where the assumptions must be made or else we'll get nowhere. So we're coming over to this and we're going to do we've got to do these assumptions. What we're really after is something called plane wave propagation. These are waves that are launched, aren't coming back, but they're planar in nature. And I'll explain that in a second. First thing we do, these are assumptions, we assume that the charge density in the region we're talking about is 0. Now that assumption has implications. If the charge density is 0, do you remember the divergence of V is equal to rho V? Do y'all remember that? Right? Well, if the charge density is 0, then div D is 0. If div D is 0, that means divergence of E would be rho V over epsilon by virtue of the fact that D is epsilon E. You agree with this, everyone? I know I'm not trying to throw it at you too fast, but I don't want to spend a whole lot of time just restating what I put down a second ago. With me, class? Take a moment. Now, if that's the case, this is 0 and this is 0. What happens over here? Take a look. Divergence of E is 0, right? What's the gradient of 0? 0. A gradient implies a derivative or a rate of change. If it's 0, it doesn't change. This goes away, which is nice. Follow me? Now I have this equation. Now this is important. This equation can have many different forms of solution. I'll explain one thing. See that gradient, that del squared of E? That is a vector Laplacian. It is not a scalar. If it was a voltage, it would be a scalar. A vector Laplacian has for both R, let's say if it was in spherical, or no, I'll say in Cartesian. If you have an X, Y, and Z E component possible, so you have EX, EY, and EZ. You also have 3 derivatives of EX with respect, or you basically have to take a double derivative of EX with respect to X, plus a double derivative of EX with respect to Y, plus a derivative of EX, a double derivative of EX with respect to Z, just to get the EX component. In other words, there's going to be 9 components of this, not 3. Remember, if it was just a voltage, it would be a second derivative of V with respect to X squared, plus second derivative of V with respect to Y squared, plus the second derivative of V with respect to Z squared. Well, no longer. Because that E is a vector, and Dr. Wentworth's book kind of ignores that, doesn't deal with it, but I'm telling you, you can't just assume things there. So what we do here is something, we're going to assume at this point that we're going to be talking about a solution here where the electric field only will have one component. Admittedly, this is sort of like knowing the solution before you do the problem. But I'll just show you what I mean by that. I think you'll appreciate what I'm saying. Here's where it is in the book, by the way. At the graduate level, if you get doctoral level courses especially, you go through the whole 9 yards with this cylindrical, spherical, and Cartesian coordinates, and then there are actually 11 separable units. There's toroid, spheroidal, there's all these weird coordinate systems that are orthogonal. But, God, mathematics take a long time to get right. All right, so in here, what we're talking about is something that Dr. Wentworth's book will call propagation, plane wave propagation, and this is on page 322 and 323 in his book. It's really chapter 6, plane wave propagation, but I'm going to just tell you this. All right? At this point, you're going to have to just trust me. What we do is with this equation, we're going to solve it, but I'll tell you, I'll just break this down for the X. I don't think he does a vector Laplacian, he's got a scalar Laplacian here. If you look at the back of the book, if you have a book with you, Laplacian is at the bottom there. But that Laplacian is called a scalar. It shows it in terms of V. V is a scalar term, it's a voltage. It doesn't work for the general form. So what we're going to do is this. We're going to assume that the E field itself, I won't write all the terms, there's 9 terms to that, Joe. The E field itself will only have an X sense to it. So we're assuming that the E field itself has a vector sense in the X direction. That is the orientation. You all with me? So remember, E field's a vector. It's got magnitude and direction. And we're going to say it only varies in the Z direction. You all with me, class? So it only varies in the Z direction, which means this is going to be times some function of Z. Maybe I can call that E naught. And I just want to make this simple for you. Now we're assuming it varies in Z and it's oriented in X. In other words, what we're doing is looking for a plane wave propagating with only one orientation for the electric fields component, and it's propagating in only one direction. Now, admittedly, this is a simplification, but it works perfectly for plane or for propagation a long way from the source. So if I look at this here and take that right here, I get this del squared of E right there, and it's going to be, now I take this to the other side. Wait a second. Actually, that's a minus sign here. Should have been a minus sign. Now when I take this to the other side, I get del squared of E minus gamma squared of E equals 0. And I'll just say this, if you just talked about the X component of the E field here, then it would be the second derivative of EX with respect to X squared plus the second derivative of EX with respect to Y squared plus the second derivative of EX with respect to Z squared minus gamma squared of EX equals 0. You see how I wrote that thing? And this is for the EX component. There would be this replicated, only it would have EY. All right, still 3 derivatives, and then replicate it again and have EZ. Y'all follow me? It's a pain in the butt to solve those things generally. As a matter of fact, I don't think you can get closed form solutions in general for an arbitrary system like that. Unless you do it numerically, then it's not closed form anymore. But we're going to take a look at this one, and I made the statement that this is only function of Z. Do you see this here? It's only oriented at X and only varies as Z, so it gets rid of these first 2 terms. That's my point. And I'll admit, it gets a little irritating sometimes. So this is going to be, are you with me? Now that's a second order differential equation, it's homogeneous. If you haven't done a lot of Diffie-Q work, don't worry about it, but this is like a standard thing you should know when you go to industry. When you take a look at this, how do you solve differential equations in general? You say, you know, X is no different than time. Suppose it was a time domain differential equation. How do you solve it? Begins with an L. Laplace, right? Sure, take Laplace transforms. That was the godsend. Beats the heck out of integrating factors in series solutions. Do y'all remember doing this? Yeah. Well, you could do it that way. As a matter of fact, if you did this, now remember, time is just a constant. When you transform something from a time domain differential equation into something, the S domain is abstract. Right? If you take a look at this, that Z, the derivative with respect to Z, could be like a second derivative with respect to T. You with me? So you would get an S squared, right, times E of X, and then you would get 2 other terms if there was any kind of value at T equals 0 or X equals 0. You could do it that way. I'm going to just do this. I mean, I don't want to confuse you on this one. If I take everything to one side, I get second derivative of E X with respect to Z squared right here minus gamma squared EX equals 0. And you know that EX, something to do at least, EX has, because it's homogeneous, has to have the form of some constant that I'll call C, and it would be times E to the lambda Z. Do y'all remember this stuff? Because it is a what? It's a homogeneous differential equation, and it's linear, so you can assume solutions, right? You take derivatives. When you do the, and Whitmer's book does this, when you take two derivatives, you're going to get a del squared here. You're going to get lambda squared coming out. And make a long story short, when you take two derivatives of this, you're going to see lambda squared minus gamma squared times, and then since this is the assumed solution, CE of Z right here, and you find out that you get lambda squared minus gamma squared equals 0 as a solution. And that means, if you take a look at this, you get lambda, make it a long story short, I'm not going to go that route, I'm just going to do this. By this time, you know, you're going to get basically possible solutions, or it's going to be some value E0 plus e to the minus gamma z plus E0 minus e to the gamma z. You can put that in there, do the derivatives. Trust me, those are the possible solutions. This should be e to the minus right here, and this is going to be a plus here. Do you remember this basically, class? Remember that gamma is equal to alpha plus j beta, and I want to make note of this. How many remember seeing something like this before? All right? This is a propagating wave, and it's only propagating the z dimension. So what we're talking about is this. If this is the electric field strength in x, and this is z, then this would be something propagating in the plus z direction, and this wave would be propagating in the minus z direction. Take a look at that. Are you with me on that? And some of you will, well, how do you know that? Well, if I take this and I wanted to bring in the phasor in, I'm going to. I would multiply it by e to the j omega t, correct? And then I take the real part of it, right? Same with that. When I'm done, here's what happens. Now in the time domain, I get e, this is the x component, e of x, and this would be a function of both z and t now, not in the phasor range. When you go ahead and do that, you're going to get e naught plus, then would be e to the minus alpha z, right here, and it's going to be times cosine of omega t minus beta z, and the next term, I'll get out of your way, 1 second. The next term is going to be plus E0 minus e to the plus alpha z times cosine of omega t plus beta z. This is propagating in the minus z direction, this form. This is propagating in the plus z direction. And if I asked you, how would you figure out which way those terms are propagating? Anybody?
The sign on beta? On B?
The what?
The sign of...
Of beta, you're right. What he's saying is the coefficient of beta right here. One's negative, one's positive. Now here's the real truth. You always make things simple for yourself. So let's assume alpha is 0. So alpha being 0 means it's lossless, by the way. Alpha is 0, and we look at just this. If we plot simply E x is equal to some E naught, and then forget that, cosine of omega t minus beta z. Y'all see that right there? That's the one I said it's propagating in the plus direction. All right. Y'all with me? I'll show you a couple ways. Take a look at this argument. We're going to call theta. Do you agree that theta right there is the argument omega t minus beta z? It's whatever the argument, cosine is something, it's got to be an angle. So that's omega t minus beta z. Agreed? That would be the phase. And when we look at something propagating, just think of a surfer on a wave. Doesn't matter if the wave is electromagnetic or if it's an actual physically observable phenomenon like a wave on the ocean. Just think of a surfer on a wave. The crest of that wave should be approximately the same height. It may decay, but the surfer's on that and he's surfing just in front of the peak, right? He's just in front of a constant phase point. You with me, class? The phase of that thing is constant. It's moving, but it's a constant phase. So what you do is take a derivative of this with respect to t, of the phase of that argument, set it equal to 0. So now you're going to see how fast that phase is moving. When you do that, you get what? Omega minus beta times dz dt equals 0. Do you agree with that? Are you with me? What I've just done, I'm figuring out how fast that point's moving. Look at dz dt. Isn't that the phase velocity? The rate of change of z with respect to t at the constant phase point is the phase velocity. So that means that when I take a look at this, omega would be equal to beta times v phase, or phase velocity is omega over beta. Some of you people remember that, right? You'll notice it's positive. You all see that? That's moving in the positive z direction. And that's one way to figure it out. Another way is just plot points. Simply let t be 0 and plot versus beta z. By the way, cosine of minus beta z is an even function. Okay? Then let t increment a little, and then plot it again. And you're going to find the head of that wave is moving to the right. You with me? You can do it any way you want, but that's guaranteed to work. All right, class? So that's how the wave's moving. And that happens to be the phase velocity. While I'm at it, since I need to do this review anyway, that's phase velocity. It's equal to omega over beta, right? What's wavelength? That's a symbol for wavelength. What's the wavelength? I want to make sure you guys see this. Just think about it for a moment. Force yourself to try to, this is over 230, right? Okay. Yell at me if I get too far ahead. All right, with me, class? So if you think about this, how would you get wavelength? Well, I just figured out phase velocity by how fast the phase is changing. Let's go ahead and do this. It always will help you learn is to force yourself to ask yourself a question. Think about it. If you don't know the answer, then listen. You need to have that question in your mind, not just looking at stuff as it's coming at you. So how do you get the actual wavelength? Well, if you think about this equation right there, again, I'm getting rid of alpha, right? And that's a forward propagating wave, right? Now, we're after wavelength, right? Let t equal 0. So if t is equal to 0, then I get e of x is equal to some e naught, right? Times cosine. Technically it's minus beta z, but cosine is an even function. So I might as well say cosine of beta z, correct, class? You all with me? So now plot it versus z. I want you to follow. So, well, what does it look like? Well, it starts, cosine of 0 is 1. It goes down, and then it repeats itself, right? You all with me? That's a cosine waveform, right? What's the wavelength? Wavelength is what? The distance over which it repeats itself, right? The distance it takes before it starts repeating itself for a periodic waveform. With me, class? Well, what is that? Think about this. That's the argument here is 0. The argument beta z at this point would be 2 pi. You all with me, class? So I simply say 2 pi there is equal to beta times z, but not z, lambda. Because that would be the point right here, that would be lambda, would be one wavelength. Y'all with me? And that's how you always get wavelengths. So wavelength is 2 pi over beta. And that's true always. And that's important, because you're going to see that beta, boy, you're going to see this phase velocity, and we can talk about that shortly, and a good conductor can be much, much less than the speed of light. Much, much less. And the wavelength can get it can be getting angstroms, if you know what an angstrom is. I mean, you can't believe the crazy kind of physical implications of some of this stuff are at very high conductivity, for very high conductivity materials. Okay. Got that. Next. Any questions? This is just theory so far. How many have seen most of this before, or at least in physics, or, I mean, some of this stuff is actually very similar to what we do with transmission lines in the EMAG one. Okay. This is chapter 6. So, next, all right, I did the time harmonic stuff. All right, next we're going to take a look at the H field and then get something called the intrinsic impedance. So, here's, sorry. The way a lot of this stuff becomes, at least you appreciate it more, is when you see problems done solving. Okay, now we're going to take a look at this. So I just said that the form for the E field, I want to stick to the phasor. So the vector phasor form of the E field for propagating waves, propagating in Z direction, but only have an X orientation. It's going to have some value, E naught. It's going to be minus, and it's going to be, e to the minus gamma Z in the AX direction. The units would be volts per meter. You with me on that, class? And now I know that curl of E right there is equal to minus J omega mu times the H field, right? I'm writing down Maxwell's equations, but I'm going to keep it in terms of the phasor domain, and I replace B with mu H. Okay, everyone? With me on that? Okay. Now, what is the curl of E? Well, you can look it up in your book, right? What is curl of E in general? Do you remember how to do curls? I don't know. If it's just X, Y, and Z, you do what? You do this crazy AX, right? AY. Does he show this in the book? I think he does. DDX, DDY, and DDZ. And then, well, the E field only has an X component, right? 0, 0. That would be the curl of E if the E field is only an X component. Agreed? In general, it had Y and EZ there if it was. So what's the curl? Do you remember doing this kind of stuff? How many remember this, right? It's a determinant, right? Do you remember getting it or not? Look in the back. Do you have your book? Who has your, bring your books if you have them. If you look in the back of your book, hopefully, this book has, my book has seen better days. See it? It's at the bottom of the page, the inside cover right there. Can you see it? Do you have a book or not?
Not with me.
I mean, you do have one though?
PDF.
All right. It should be down, you should be able to see it. I don't know about the PDF. I would assume that you have it. But, anybody looking on the PDF?
I'm looking for it.
It should be at the very back. The reason I'm saying is I don't know what you have. I really don't. The book has it. I know that. I'll send you a bunch of stuff. I'll send you the actual vector Laplace and all that information too. And the reason I do is because it's useful with waveguides and some of the stuff we do to get the actual vector Laplace. Okay. Now back to this thing. When you do a curl, what happens? Well, I got ay ddz of ex, so this is going to be d dz of ex, and it's in the ay direction. And then when I go back up this way, I have d dy of ex, but e is only a function of z, right? Remember that? So this derivative, the minus d dy of ex times az, ex is not a function of y, so that derivative is 0. So this is the curl of E. Remember, that's the E field, so the curl of E means I have to take a derivative of this with respect to z. So that means I get E naught, just watch this, E naught. And then I get minus gamma coming out. Remember, that's a z here. Then I take this and multiply by e to the minus gamma z right here. And it would be times ay is equal to minus j omega mu times h. Can y'all follow me? Just take a moment. Y'all, can you read my writing?
Are you just taking the derivative?
Well, this is the curl of E, right? The curl of E is right here. So I'm taking the curl of E, and this is the E field we found, so we're putting it in there, taking the curl, this is what comes out of it. Now, if you look at that, what does it mean? Well, I can get rid of that negative if you look at that. It appears on both sides, right? If you take a look at this, that means the H field itself is going to be some E naught, and that's going to be times gamma times e to the minus j gamma z over j omega mu. And that would be the H field. So the only thing I've done is take this side and divide by j omega mu. Did y'all see this, class? Now, here's what we do know. Because this is in the phasor domain. We can say what really goes on is I'm going to have the E field, some E naught, times e to the minus gamma z. That is this E field. You all see that, class? I factored it out, and I'm dividing it by this stuff, which is really dividing by j omega mu divided by, and in this case, it would be divided by gamma. You all see this? Because divide top and bottom by gamma, you get over G. You with me, class? And it would be in the AY direction. Erase that. So what is the ratio of the E field over the H field? We use impedance. Remember the definition of impedance in circuit analysis, it was voltage to current. Do y'all remember that? Well, the E field has the units of volts per meter right here. And the H field is amps per meter. So volts per meter divided by amps per meter would be ohms per meter, or the characteristic impedance, all right, or the intrinsic impedance of the media. And here's what happens. We define eta as, and this is eta, I'll just call it eta, is going to be equal to the ratio of E over H. So it's the ratio of that E field over the H field, and it gets rid of the E to the minus J, E to the, should be minus gamma Z, not minus J gamma Z. And that becomes equal to simply J omega mu over gamma. So let me go through and do this way. So it's J omega mu over gamma. And what is gamma? Well, gamma is equal to the square root of J omega mu times sigma plus J omega epsilon. Now take a moment. Do you remember this? That was the complex constant I made, gamma. Take a moment, class. I know this stuff's kind of, it's a lot to swallow in one episode. you might say, but you're gonna have to swallow it, so I might as well take a look. You with me, class? Now, just look at this for a second. You see how those J omegas both appear top and bottom? So now we say this, and this is called the intrinsic impedance. Is equal to the square root of J omega mu over sigma plus J omega epsilon. And that is the intrinsic impedance in general. And let me erase this. If you had me for EMAG 1, I usually cover this in EMAG 1, near the end of the lecture, into the course in EMAG 1. But look over here now. So for a forward propagating wave, a wave going the plus z direction, the ratio to E of H, and this is only for plane waves propagating, this is only for propagation, or E plus to H plus will be equal to eta, which is square root of J omega mu over sigma plus J omega epsilon. But if it's propagating in the negative direction, then the ratio of E0 minus to H0, or E minus to H minus, will be minus eta. And the reason is because when you take the actual curl that's propagating in the opposite direction, you won't get a minus gamma, you get a plus gamma, or coming out in front. You're just going to have to take my word for that, and you'll see that. So anyway, key thing is the intrinsic impedance right there is a ratio of E to H, and it's positive for forward propagation and negative or for waves propagating in the opposite direction. But it really just has to do with the signage. You'll see more information about that later. So let me just give you some values so you can see this. If you look at this right here, what if we are in free space? So if we're in free space, that means sigma 0 and epsilon is equal to epsilon naught, and mu is equal to mu naught. Basically a vacuum, that's what free space is. You with me? So if you're in free space, what's the value of the intrinsic impedance? Take a look at that. It's the square root of what? J omega mu, sigma 0, right? Divided by J omega epsilon. You all see this, class? Sigma 0. You notice the J omegas kill each other off. They cancel. And so you get what? Square root of mu over epsilon, right? Now, mu is 4 pi times 10 to the minus 7. Epsilon can be rendered as 1 over 36 pi times 10 to the minus 9. It's just another way of stating it. It's an approximation. But this ratio will be exactly very close to 120 pi ohms. Follow me? How many remember that? All right, now that's free space. One thing also to take away from this, if sigma is 0 and it's lossless, that's what sigma equals 0 implies. It's always going to be equal to a ratio of mu to epsilon. So you can take this and say it's really equal to, if it is lossless, you can say it's square root of mu relative over epsilon relative times eta naught, and just leave this as eta naught. And that's the intrinsic impedance of free space. Okay? Okay. Okay? Next. Alright, so have your books with you, but bring them for Monday for sure. So I'm going to do two things. We're going to get to propagation and lossy regions and stuff like this, but I want to do something that's a little bit forward. This is on page 327 of the text, but it shows you some tricks you can use to make life a whole lot easier finding E and H without doing curls. Now, curls are something necessary to know for the general form, but for propagating waves, when you have plane wave propagation, you don't need to do curl after curl after curl and go bananas. Because some of these things take a while, and you can make a lot of silly mistakes. This is important. These are two relationships that are on, whatever page it said, on page 327 that are so important. When you take a look at curl, instead of the curl equations, you can do this. If you want the H field, this is in the phasor domain, and it's assuming plane wave propagation. Remember this whole chapter, we're talking about waves, plane wave propagation. I need to define that a little better in a second. These are two things. The H field will be equal to 1 over the intrinsic impedance of the media, and then it's going to be times the unit vector in the direction of propagation. That's what this is. And it's crossed into the E field. And this is in a vector phase, and I'll talk about the E field's got an orientation. The direction of propagation is the way the wave is moving, the direction it's moving. And if you have the H field and you wanted the E field, it's minus eta times a unit vector in the direction of propagation crossed into the H field. You can always get them. And this is for plane wave propagation. How many remember that? Any of you? I think if you have me for EMAG 1, I think I did this. And I did it in EMAG 2, I have to.
Does the squiggly line on top mean it's a propagating wave?
No, it means it's a phasor. Doesn't Gross use that for phasor? Who had Gross in here? Remember him? It's a tilde generally means phasor, but you know what? Anytime you see a J, you know you're in the phasor domain because time domain doesn't have J. That's the easiest way. Okay. Now, if you look at this, we're talking about plane wave propagation, but something I didn't say about plane waves, and I try to do it as simple as possible. Suppose I want to explain plane waves. What is a plane wave? Well, I said the E field itself is only in one direction, its orientation is propagating in one direction. I'm going to try to give it an analog or an analogy of this in the physical world. Think about dropping a pebble in a puddle. There's waves that propagate outward, right? Ripples. Well, those ripples are moving at a relatively constant velocity away from the center where you drop the pebble. And if you assume that the height of the ripple, or the height it is likened to the electromagnetic field intensity, and the vertical movement is, the wave is propagating horizontally, but the surface movement is only vertical. Do you follow me on this guy? So if you think about this, if the pebble drops here, and as the wave propagates out, first the circles are tight, then the radius of curvature that these waves are on keeps getting larger and larger. Pretty soon, if I'm out here, I'm surfing on that thing, or I'm on it, it's one big plane, right? It's just one wave with no curvature apparent, right? And the wave is moving in one direction, but it looks like it's just a plane. There's no indication of any curvature. That's what a plane wave is. Think about it. The puddle variation is in one direction. It's just the vertical height changes, but it's propagating. If you get far away from there, and only one direction too. So if you're a long way from the event that caused it, an antenna, Weagle FM, then you can assume wave propagation is planar. That's the idea. And we can argue about how far that wave can have to be. It depends on what you're trying to do. Curvature is something that has, only time it's of meaningfulness as meaning is when you're talking about other events that could have a different time perception associated with it, if the curvature was different. Anyway, so those will get you the stuff without the curl for plane wave prop, which is nice, right? Let me do an example of this. And I want you to work with me on this. Suppose we're in free space. So we're in a vacuum. And I have this as an E field. In the phasor domain, E field is equal to 20. And this is in free space. And I'm going to say it's E to the minus J 10Z and the AX direction. So this is a wave, it's in the phasor domain, it's propagating in the plus Z direction. With me? Just look at it and think about this now. What is the magnitude of E? Magnitude. Just look. This would be in units of volts per meter. Class,
20.
can you read my writing? What is it?
20.
It's just 20, right? E to the minus J, anything has a magnitude of 1, correct, class? All right, what is beta? Just by looking.
10.
Can you read it? 10. What is alpha?
0.
It's 0, it doesn't exist, right? It's 0, correct? All right? All right, which way is it propagating? Say again? Which way is it propagating?
Z.
AP, in the Z. You see it? How did I get that? I looked up here. There's beta, right? This is beta. So if that's a minus J, it's going the plus Z direction. With me, class? So it's going in the plus Z direction, plus AZ. All right, keep looking. What is it? Now, I mean, at that point, it's that we're done here, right? We need H. With me? And by the way, since we're in free space, eta is just 120 pi, about 377. Agreed, class? Ohms. So what's the H field? Well, it's 1 over eta, so it's 1 over 120 pi, right? Unit vector and direction propagation is AZ, correct, class? And that's crossed into E field, right? I gave you that E field, which is 20, right? And it's going to be E to the minus J 10 Z AX, right? This is a classic example. Are you with me, everyone? Do it with me. So what do you get? Magnitude of the H field here is going to be 20 over 120 pi, and that would be amps per meter. You agree? All right. Now I got A, well then I can put the E to the minus J 10Z here. By the way, the variation in radians per meter will be the same for H and E. Has to. If you're talking about a plane wave, E and H are intimately linked. One can't exist without the other if it's propagating. Now, when I have AZ crossed AX, what do I get? Think about it. Z crossed X is
Y.
Y, right? It's not Jeopardy, right? So it's a Y. There's something I like to say right here, and I know I'm probably about out of time. You're not going to text me, are you, Andrew? You're out of time. All right. Remember this. If you have a right hand, I hope everybody does. If you take your index finger in your right hand, put it in the direction of the E field, and then cross it into the H field. Just take it and rotate it into the H field. Your thumb on your right hand will point in the direction of propagation. We already knew the direction of propagation. But it's a handy thing to remember. It's called E cross H is direction of propagation. E cross H formally is a pointing vector. I don't have time to do it today. So if you notice that, I got E in the X, it's propagating in the Z, right? But my H field, it better be in the Y, right? And it surely is. See it, class? E cross H is direction of propagation. With me? Okay. Am I out of time?
Yeah.
Anytime people pick up phones, I'm thinking, because I had one kid used to do this. He'd text me, hey, you're almost out of time. You're right there. Just. Actually, I got this. That's the second chair. I'm standing right there. People don't want to be noticed. They'll text the crap out of you and get your phone going off. What? Just raise your hand and say something. All right, guys. I'm going to put some homework up for you. See you Monday. If you got questions, come on. Do you all understand that?
Yeah.
It's a lot, but it'll make sense as you start working problems. Thank you again.
Yeah.
Who's going to have those questions?
Yeah.
Yeah.